In this third video about the control lab, we're going to talk about the implementation of a control structure with PID plus feed forward. As you might have noticed, the responses of the system, so of TCLab, are rather slow. So we are not going to test this control structure on TCLab. We're going to test it in simulation first. And for that we need, of course, a model of TCLab. And this is why we start with the construction of this model. In order to construct this model, we'll open the library process. So just open it and this is what you'll obtain. You will notice that this library is locked, so you cannot do any changes unless you decide to unlock it. So unlock it, and now you double click and you see here unlock library. So now this means that you can do changes. So what do we see in this library? We have here a block TCLab that allows you to connect with the actual system. So if you double click, this is what you will see, and here you have the software that allows Simulink to connect with the actual process. And here you have a so-called configurable system. This is a block that you can find in the library browser. Should have started it before. Under ports and subsystems, here it is, ports and subsystems, and then here you have configurable subsystem. And this block can behave as, well, different blocks that you have here in your process library. So for the moment we only have one block here, TCLab. So this block can only behave as this block over here. But if you add blocks, they have to have the same number of inputs and outputs and the same denominations. You can add members to this configuration block, and this block will be able to behave as any of the blocks that you have constructed. So what we'll do here is add a block. We'll simply copy this one and paste it. We'll give it another background color. Let's say that we use cyan, and we'll give it another name, and we'll call it TCLab model. Right? Well, when you copy a block in the library, this one is still attached to this one. So what you need to do is right click and then library link, disable link, and then again library link, break link. So now this block is completely separated from this one. What we can do now is go in the block and we remove everything that is in between the inputs and the outputs. What you need to do now is construct our model of the process using the results of the identification. Remember that we have identified the input-output transfer function using, well, optimal identification, right? This is a Van der Grinten system, again, 2 time constants and delay. This is POS, the input-output dynamics, and we have something similar for the disturbance dynamics. So we'll use this to construct a model in between the 2 inputs and outputs. So this is the model we have to construct in this transfer function PFS, and it will also be the case here in the transfer function DFS. Well, we have a Van der Grinten system, so we need a gain, 2 first order systems, and a delay. We'll have something similar over here. We'll have to construct this deviation from 50%, so will have an add operation, right? And remember that the signals that are coming in are digital signals, and the signal that is leaving is a digital signal. So here we have something that is continuous time, so we'll need a digital to analog conversion, right? So we'll have to take into account the zero order hold mechanism, and here at the end we'll have an analog to digital conversion, and we'll be able to emulate this in simulating using a so-called rate transition. Well, let us now select the blocks that we need in the library browser. So what we need are blocks coming from the continuous time library. So we'll need a first order system, we'll need a transport delay, right? We'll need some blocks from the math operation, so obviously adding operation, gain, right? From discrete time library we'll need, well, a zero order hold mechanism, right? And from the signal attribute, I think here it is, we'll need a rate transition. So from this here we'll be able to construct the model, and here is the model that has been constructed. I've used a few other blocks that I forgot to mention. In discontinuities I've used the saturation. Remember that the heating power is limited between 0 and 100%, so you should take that into account in your model. And from sources I've used the constant block over here, here and here. Well, let us have a look at this model more closely. So here we have this saturation. As you've seen, I've limited the heating power to 100% and 0%. You have something similar over here. Here you have the heating power. Remember that in this branch over here, where you have the disturbance input is the deviation from 50% heating power. So this is why we subtract 50%. This is these are digital signals, so now we need a conversion, and we need to take into account the zero order hold mechanism, and this is what this block is doing. It is very, very important that you set the sample time TS. Remember that in the variables.m file we have set TS to 1. And then you have, well, the dynamics. This is a first order, right, with gain Kp, time constant T1. Here you have something similar, but it's Kd. It's the gain of the disturbance dynamics, and T1d, the main time constant of the disturbance dynamics. So here you have a first order system with gain 1, second time constant of the input-output dynamics. You have something similar over here, but with the time constant, the secondary time constant, coming from the disturbance dynamics. Here you have the delay, right? Theta and theta d. And then you have to add the two branches. At the output, you have a rate transition because you go from analog to digital. So again, it is very important that you set the output port sample time to TS. The output T2 we do not need, and we do not simulate it. We'll simply set it to 0. And now we still have to discuss here this adding of an offset to make everything right, so that we work around the correct working point. So where is this offset coming from? Remember that we are working around a working point that we have determined experimentally. We have set MV and DV to 50%. We have waited for a steady state, and we have seen that PV0 is then 75 degrees Celsius. we'll assume now that dv is equal to dv0 is equal to 50%, so that we only have to take into account the input-output dynamics. But we can see here, because the gain, and the gain here is in degree Celsius per percent heating, because of this gain that is roughly 0.6, that in steady state we'll have a PV that is Kp times mv0, and this will be around 30 degrees Celsius, right? But we have determined experimentally that the PV0 is 75, so we need to add 45 degrees Celsius to bring the model to the correct working point, right? So you can see that I've added a line here to compute this offset, and this offset working point is simply PV0 minus Kp mv0, and this should, well, compute something in the neighborhood, as we have seen, of 45 degrees Celsius offset. And if you run the M file, you can see that indeed we obtain an offset of 45.5 degrees Celsius. So our model is ready, right? So we have now our model that we can use for the design of our controller and to test everything in simulation. And when we are ready, we're going to switch to the actual platform. The only thing that we need to do is click here on this configuration dialog, and we have to add another member to this configuration block, and it's this TCLab model. So apply, OK, and we save. So we have now a model process, right? A block process that can behave as this block that allows you to interact with the actual system, or it can, well, behave as this block that allows you to simulate TCLab. So if we now return to our TCLab identification file, this is what we obtain. If you double click, you see that you're still using the block that allows you to interact with the system, but if you right click, you'll have block choice, and then you can go to TCLab model, right? And if you now double click, you obtain the model of the system. So this will allow you to, well, simulate the system and to do the same type of experimentation that you did on the actual system. Well, let us redo this first experiment that we did, but in simulation. So remember that we keep dV, the second heating power, to 50% here, and what we'll do is bring the first heating power to 30% and then do a jump of 40% so that we go to 70%. So this jump will take place in 800. So from 0 to 800 we'll apply this 30% heating power so that we go to a steady state, and when we are in steady state we add 40% so that we have a jump to 70% heating power, right? So this we can now simulate. You can see that this is very fast. We have just simulated 2000 seconds and we can look at the response. And you can see here that indeed we go to a steady state and then we apply our jump, the same jump that we did experimentally on the actual system, and this is what you obtain, and this is very similar to the step response that we had obtained on the actual system. So we are satisfied with the model that we have implemented. Well, we can now save our model, and remember that if you want to test on the actual system again, well, you'll need to change the configuration and you'll need to go to TCLab, which is experimentation on the actual system. So this concludes the first part of the control lab about identification, right? And well, the second laboratory, third and fourth laboratory will be dedicated to the design and implementation of a PID controller with feed-forward structure. So since this is working, what we'll do is rename this to identification, and we'll prepare a new folder by simply copying this one, and we'll rename it to PID feed-forward. If we go in this folder, there are a number of things that we can delete. Yes, we won't need everything that has to do with identification. We don't need the mod files, the PDF files. This one we can delete as well. So we do a general clean up, right? And we'll call this one TCLab PID feed-forward, right? And then we can open it, and what we can do is remove these buttons over here because we do not need them anymore. So what we'll do now is design a PID controller plus feed-forward structure for this model, right? So you'll have to work in a simulation first, and when everything is working, using this block choice, you'll be able to, well, implement your PID plus feed-forward on the actual system. In the meantime, I've implemented the PID controller with feed-forward structure so that you can have an idea of what you should obtain. You recognize here the model that we have obtained after identification, right? Of course, here it's in the configuration model, so it's used for simulation. And here you recognize the feed-forward, right, plus PID controller, and the goal for the second, third and fourth control lab is to implement this in simulation first, and then to actually implement and test this control structure on the actual system. Well, let us first start with this digital PID controller. The theory behind all this can be found in, well, the last section of the course. It's a PID controller with a manual mode, and that allows you to have a feed forward entering the block. And of course, if you look at the faceplate here, you have of course saturation of MV that is implemented, right? So what you have to do is code this block, and to help you, I've given you an example. It's a digital first order system. Actually, the first video dedicated to the control lab is about this first order digital system, and in this video I'll show you how you can, well, code this first order recurrent equation from scratch. So you'll have to do something similar, of course, for the PID controller, and well, the recurrent equations can be found in the theoretical course, and the explanation is given in the videos. Remember that you should not forget to set the sample time for this MATLAB function so that it runs every t of s. The tuning of this PID controller should be done using the IMC tuning method that is also explained in the theoretical course. Well, here you find an algorithm to code the PID controller using the Euler backward difference approximation. You'll find a similar algorithm for the trapezoidal approximation. So as you can see here, you can compute the output of the PID controller, and as you can see from those two recurrent equations, you'll have to keep track of the previous MVI and the previous MVD and the previous control error. So you'll have to define persistent variables that are kept in memory for MVI, MVD, and the error, so that to compute MV at the next iteration, you have access to the previous MVI, the previous MVD, and the previous control error. Of course, you'll have to integrate a manual mode as is shown over here. Remember that the code that is given over here does not take into account derivative action and feed forward action. Refer to the videos dedicated to the PID controller for more explanation. There is an actual implementation of a PID controller on a PCS7 Siemens system. You can use this example to better understand what you should do. You should also implement, of course, actuator saturation in such a way that there is no integrator windup. This is also explained in the slides and in the associated video course. Remember that here again, derivative action and feed forward action is not taken into account. Well, here you can see the feed forward. It is connected to the feed forward input of the PID controller, and of course this is here a digital implementation of the feed forward. Remember that this feed forward is acting on a deviation of dV with respect to dV0, so a deviation with respect to 50%, right? Do not forget to subtract here 50%. So here you recognize the feed forward structure. The theoretical background is given in the slides and the associated videos. You have two lead lags, a delay, and the feed forward gain is of course hidden here in this lead lag, as you can see over here. Right, so what you should do is implement this lead lag in the same fashion as this first order system is implemented. Remember that I've given you an example on how you can implement a first order using recurrent equations from scratch. Well, you should do something similar for the lead lag. Of course, test your lead lag system separately by, for instance, considering a step input. Make sure that it works and then integrate it in your feed forward. Again, do not forget to make sure here that the sample time is set to TS. This is a mistake that is very often made. So here you have the gain, first lead lag, second lead lag, and what you have over here is a delay, a feed forward delay. The explanation of on how to compute this delay is given in the videos. Again, do not forget to set the sample time. This is a digital controller with feed forward, so you should make sure that everything runs at a sample time TS. When you have implemented this feed forward and PID controller, you should have a Simulink file that looks like this. So this is the recurrent equation that you'll have to implement for a lead lag system, at least if you're using the Euler backward difference. Well, if you look at the changes with respect to the first order system that I've given you, for the first order system you had to keep track of the previous output. Now you'll have to keep track of the previous input as well. So this means that you'll have to create a persistent variable, which is the previous input. Of course, you can, if you want to, also implement a lead lag system using the trapezoidal approximation. This is a kind of originality that you can do in your control lab. And then of course you'll have to derive the associated recurrent equation. Well, once everything is implemented, you should check everything in simulation. As you can see, the PID controller is in automatic mode because this input man is set to 0, and what we'll do is set the set point. By the way, the set point is in degrees Celsius because PV, the output temperature, is in degrees Celsius. Well, this set point here will go from 50 degrees Celsius to 60 degrees Celsius at step time 1000 seconds, right? And this is here the disturbance value and the second heating power. And what we'll do is do a step of 50% heating power to 60% heating power at a step time 1700 seconds. So this will emulate a disturbance, and well, our feed forward should counter this disturbance. So let us test this by running the system. So this is the first time this is run, so this is taking a while, and as you can see, we have just simulated 2000 seconds, so this is very fast. So if there is a mistake, you can quickly react and correct. So this is what we obtain. Of course, it takes a while to go to this set point of 50 degrees Celsius, and here you see the jump to 60 degrees Celsius. So in your scope, what you should do is show the set point here that is given here in red, and show on another curve here the PV value, which is the output temperature T1. And as you can see, when we do a set point change, we have a nice response here, and this is the associated MV, which is the first heating power, right? So this is the so-called closed loop step response, because we're now working in closed loop with a PID controller that is active. As you can see over here, we do a change in DV. We organize a perturbation on the system by changing the heating power 2 from 50% to 60%, and as you can see, the system reacts by decreasing MV. This is the work of the feed forward action, right? And of course, combined with this feed forward action, if it's not perfect, you have the PID controller that does an additional correction. And as you can see here in simulation, at least, well, there is no influence to be seen from this change of DV. So this looks nice. So we are ready to test this, but now on the actual system. There are two things that can be noticed in the Simulink file. Well, we have run the simulation, and at the end here, DV is at 60%, so there is a deviation with respect to 50%, and as you can see, the feed forward has counteracted this, and you can really have a look at the scope. This is the action of the feed forward. You also have noticed that the links have changed colors. This is to indicate that the signals are digital signals that are run every T of S. Well, to make sure that you have access to the sample time of each signal, what you can do is go to debug, then information overlay, and you should select colors, right? And this is going to make sure that you see what is the sample time of each signal. As you can see, I've connected the TCLab platform to the PC, and it's now time to test the PID controller with feed forward on the actual platform. So what we'll do is choose the actual platform, TCLab. You can check this and see that indeed everything is ready to connect with the actual system, and we'll put the PID controller in manual mode with a manual value of 50% of heating power to MV, so the first heater, and we can now run the system. And if everything goes right, we should connect to the actual system, and you can see that this is indeed the case. We can now have a look, and you can see that MV is at 50%. The output temperature is going to increase, and what we'll do now is wait until we reach a steady state. As you can see, we have now more or less reached a steady state. Remember that the controller, the PID controller, is in manual mode, and this explains why PV is of course not on set point here given in red. It's in manual mode, this PID controller, with a MV at 50%. So what we'll do now is, well, we see here that the temperature is around 73%, so we'll switch to this set point and we'll put it at 73%, which is precisely what we observe over here. We are going to set this one to 50% heating power, and then we're going to stop the simulation, well, the experiment I should say, because we're testing on the actual system, and then start the system directly, right? So this does not have an influence. And what we'll do now is go to automatic mode. So we have here the process, right, with its set point. It's in the background, and what we'll do here is bring it back to 70 degrees Celsius, and because the set point has the same units as PV, and PV, it's the output temperature. So what we'll do now is wait until everything has settled, and then we'll do, for instance, a set point change in closed loop to 80 degrees Celsius and see what happens. So I'm going to stop the video now until we reach this set point of 70 degrees. So as you can see, we have reached the set point of 70 degrees Celsius, and what we'll do now is do an increase to 80 degrees Celsius. So you can see here the set point change. This is the, well, heating power, MV. So this is proportional action plus derivative action. And what we'll do now is wait until we have reached a steady state, and we'll come back then. Well, this is the closed loop step response that we obtain. We have done here a 10 degrees Celsius set point change, and this is the closed loop response. As you can see, we reached the set point in about 200 seconds. So the settling time is about 200 seconds. As I said before, this is the proportional kick and the derivative kick. After a while, the derivative kick disappears, right? The derivative action disappears, and well, in the background, the proportional action is gradually taken over by the integral action. This is explained in the theoretical course. So what we'll do now is, well, do a perturbation dV, right? And what we'll do is increase the heating power HP2 to the second heater, dV2 to 70%. And we should see after a while the feed forward action that starts to play. And this is what you can see over here. This is the change in dV, and what we'll do is wait a bit to see what are the effects. So I'll stop the video for a while now. So as you can notice, we have arrived at a steady state, and we can stop the experiment. As you can see, the effect of dV on PV is very small. This is the work of the feed forward action, and what has not been compensated by the feed forward has been corrected by the PID controller. So what we can do here is adjust the scales, right? So we can set it to, for instance, 80 and, well, let's say 30, and we can do something similar around here to, well, see things a little bit better. So we'll take 60 and 90, right? And then we can do something similar around here. So here we went from 50, so we'll start at 40 and 80 over here. So here now it's clear, well, there is a small deviation from set point coming from the change of dV. So of course the feed forward action is not perfect, but what has not been compensated by the feed forward is then subsequently corrected by the PID controller. Notice that this is what is coming from the feed forward, and we can actually look at the curve. So this is what the feed forward has actually produced. So as you can see, it is, well, assisting the controller by reacting immediately to a change in dV, so that the work of the PID controller, well, becomes much less important. It just has to correct for the mismatches that are due to the fact that the feed forward is not perfect. So what we'll do now is save these experimental results, right? Remember that you have to print to a figure, so you have a different figure appearing, and then you can use this command here in the command window, and so we'll call it TCLab PID and feed forward. And as you can see, this one is appearing over here, and we can have a look, right? And this looks okay. So this you can keep for your archives for the report. Well, as you can see, I've only done one set point change. You should probably do several, and you should also do a decrease of a set point and compare these, well, closed loop responses around different working points and discuss. To test the feed forward, I would like to see the following tests performed. So PI controller in manual mode, and then you do a change of DV with and without feed forward, and then you do the same with the PI controller in automatic mode. You change DV with and without feed forward, and of course I'm interested in the discussions, in the comparison of these different experimental results. The experimental results that you need to produce are described in the assignment, and as I've said, I'm very much interested in the discussions that will follow.